Okay, so in this video, I will discuss this paper. The title is Medical Forum Question Classification Using Deep Learning. Okay, so the authors are as follows. One of them is myself, right? And the paper is primarily from IIIT Hyderabad. The paper was presented at the ECIR European Conference on Information Retrieval in 2018. Okay, so let's get started. So the basic motivation of the work is that web-based information access is an integral part of meeting healthcare info needs now. Okay, so I mean, lots of people actually have started putting up healthcare-related data on the web. Also, search engines, although they can answer many queries nicely, you go to Google, you go to Bing, you search for stuff, you get relevant answers. But for healthcare queries, they are not as effective. Okay. For example, this is what happens when you search for stomach ache in Grenoble. Okay, so I mean, ideally you would expect to find some hospital which relates to this kind of, which can a gastroenterologist or some hospital that deals with gastroenterology and so on, stomach aches and so on. But what you get is symptoms of stomach cancer and stomach ache nhs.uk and so on. Not really very relevant results. Okay. Or rather, if I have a stomach ache, what do I do? That is what I want to search as a user, right? So, in fact, many question answering platforms have therefore come up because search engines can't answer such questions well. So, therefore, many question answering platforms have come up. Lots of queries being asked on such question answering platforms. Many people ask lots of questions. So, for example, these are some of these online question answering healthcare based platforms: MedHelp, Mayo Clinics, WebMD, and so on. Okay. So the key problem faced by these forums is now as follows: lack of quick answers to healthcare questions. Okay. Now a user comes up. So basically, if a user has a healthcare problem, stomach ache, and they are visiting Grenoble, so they have a problem. Now what to do? Okay. They want to search on Google or Bing and whatever. They don't get an answer. They go to some community question answering platform. They basically ask such questions. They don't get answers quickly. They want answer quickly, right? So, but that's the problem, and that is why we basically want to sort of study the problem in this, which we are discussing in this paper, classifying questions into different categories based on user intent. The idea is that even among these medical forums, there are some forums which are really focused on certain kinds of questions. Okay. Now, if you put the query onto a very relevant forum, you will get quick answers. Otherwise, not, right? And that is why that's what we try to do. Given a query, we try to figure out what kind of forum this question makes sense for. Okay. So classify the question into different categories based on the user intent. And what kind of classification makes sense? So we looked at a few forums, and also we looked at this kind of data which was shared by IEEE Healthcare Data Analytics Challenge, right? And they came up with very intuitive categories of healthcare-based questions. Some questions are just demography-based, right? For example, they are related to subgroups characterized by age, gender, etc. So, female health questions, questions for 60+ years of age, and things of that kind, right? Some forums have treatment as the basic thing that is the focus. So related to a specific treatment or procedure. So radiation-based therapies, right? For example. Some forums are goal-oriented. Now again, healthcare could have goals as well. So for example, weight management as a goal. Some forums are pregnancy-oriented, so related to pregnancy difficulties with conception, mother and unborn child's health, and so on. Family support forums, where things related to issues faced by caregivers. Now, of course, patients have health problems, but caregivers have equal problems as well, right? Especially when the patient is in hospital for quite some time, and there needs to be a caregiver to support them for a long period of time. Socializing kind of forums, so where related to socializing, including hobbies and recreational activities, especially for patients with long duration diseases, right? And finally, disease focused forums, so related to a specific disease. So if I have diabetes, I would go to a diabetes related forum and ask my question. I would better go to such a forum and ask my question rather than asking, let's say, in other forums which do not have a particular disease as their focus. Okay, so to recall, the problem is, given a question, I want to figure out where to ask that question. So what is, which of these 7 categories the question fits in. Okay, here's that. Now, there has been some related work in the past, and as follows. So whether the question was asked by healthcare professionals or consumers. So not really directly related, but somewhat related. So given a question, whether it was asked by a healthcare professional or was it asked by a consumer. Okay. If the question is patient specific, general knowledge, or research related question. So again, some sort of classification of the question, but at a very broad level. Is it patient specific or general knowledge or related, research related? If questions are related to healthy lifestyle, diagnosis, health provider choice, treatment, epidemiology, so somewhat related again, but not exactly the same categories that we've considered in this particular paper. Okay. Then there is also related work in terms of methodology. So how have they sort of tried to solve these problems? So most of this work deals with handcrafted features like statistical features or linguistic features and so on. Statistical and category features only to train the classifier, lexical, grammatical, keyword, and statistical features. So many of these basically pieces of work deal with feature engineering as such. Okay. Now the major issues with such methodology is that no incorporation of domain-based features. So all these are usually linguistic features, NLP features, right? Natural language processing features. None of them are like medical features as such or healthcare related features. And also previous pieces of work actually considered small data sets, right? And there were no experiments with weakly supervised techniques. So what if you don't have large supervised data set, but still you want to sort of do something substantial, okay? So in this particular paper, this is like the outline of the remaining part of the paper. We will first introduce our data set. How do we do preprocessing to make the data set better? Various supervised mechanisms that we have used, weakly supervised mechanism, and finally present results and error analysis. So the dataset was provided as part of this challenge, IEEE Healthcare Data Analytics Challenge, ICHI 2016. So the organizers nicely shared the data with us, and the data looks like this. So each instance is basically contains a title, like for example, prolonged pain. So this is more like a query or a question, okay? And then there's a question body. So there's also a very elaborate or a verbose description of the questions. For example, has anyone had prolonged abdominal and back pain with numbness and tingling in feet and legs? I had my histo on way. It's a very long and verbose question, okay? So there's a question title, there's a question body, and then there's a category. So for example, treatment is the category here. Okay, so one of those 7 categories that we discussed in one of the previous slides. Okay. Now, so essentially at ICHI 2016, this dataset was launched. So of course there was a challenge in 2016. Various people participated in the challenge. In fact, 56 solutions were proposed in the challenge. Okay, the training data had 8,000 questions. Test data had about 3,000 questions, each with the title, description, and the category. Okay, so data set is balanced with almost same number of instances per category. So there is no imbalance in the data. So nicely across 7 categories, more or less, it is sort of balanced. Okay, so that's that. So however, we did some sort of pre-processing to tune the data to be usable for our models better. Okay, so this is the example of the question. So prolonged pain, and this is the elaborate description that we have. So we first concatenated the title and body of the question together. We basically just glued them together so as to basically come up with this long thing. Essentially, we also did one more step, removed all hyperlinks, special characters, punctuation, stop words from the question. Now usually these are like noisy things in any question. So we sort of removed these hyperlinks, any special characters that are present, or punctuation marks, stop words, which usually don't contribute to figuring out the category to which the question really belongs to. Okay, so effectively, we would end up with something of that sort. So essentially, just removed all those kinds of junk kind of related things. We also did case folding and lemmatization. So essentially, lowercased everything and also lemmatized things so that prolonged becomes prolonged and so on. So that things that are almost similar map to the same root word. Okay, so that's why we did lemmatization as well. These are the basic pre-processing things that one usually does on any language-based task, on any natural language processing task in that senses. Okay. So our final, after we have this entire data, we basically created a supervised learning model. The idea is to basically do a multi-class classification, a 7-class classification overall. So it's an ensemble of 3 different small pieces, right? Hierarchical bidirectional LSTM, also called as H-by-LSTM, right? Which more or less captures the semantics in the question. So LSTMs are known to capture the semantics of sentences very nicely. And Bi-LSTMs work even better, and hierarchical Bi-LSTMs are the ones which we propose, which we use in this particular work, right? Hierarchical is also called as stacked. So effectively we use stacked Bi-LSTMs with 2 layers, stacking of 2 layers. Okay. So model based on medical features. So we basically said, hey, previous work never bothered about using medical features, but medical features are so important because categorization, for example, pregnancy related features or treatment or disease related features are very important, right? So we incorporated domain knowledge by considering these medical features. And also we captured the probability distribution, lexical distribution of words by capturing TF-IDF features. Okay. So this is how now in the next few slides we'll discuss various of these small models. So let's talk about hierarchical bidirectional LSTM model first. So here is how the model looks like. So here is a representation of a question, the hierarchical representation of the question that we learn using the hierarchical bidirectional LSTM model. Okay. So each question is considered as a sequence of sentences, and each sentence is a sequence of words. So there's 2 levels to the hierarchy in that senses. Okay. So there's the first level of LSTM, which basically takes these. So essentially, first we used glove embeddings for every word. So every word is represented using glove embeddings, and then you basically first take a sentence level encoder, which basically takes each of those word level embeddings, creates an embedding for the entire sentence using a Bi-LSTM. Okay. Now then the sentence level encoder, so this is the sentence level encoder. Okay. Again, this is a stacked Bi-LSTM. So that's or rather just a Bi-LSTM here, and then you have a question level encoder. So what that guy does is to basically take encodings for every sentence from here and basically learns a Bi-LSTM on top of that. So it's like a 2-level Bi-LSTM in that senses. Okay. So then the second part, as we discussed here, was model based on medical features, which capture the domain knowledge. Okay. So for that we did the following. We extracted medical features as follows. Okay. Consider the sentence: I had undergone a CABG after a massive heart attack. What are the prognosis after surgery? Okay. Now that's the question, and of course we first figured out medical entities out of it. Now it turns out that there are nice online sources available, medical knowledge bases, like UMLS, right? So Unified Medical LS something, right? So essentially, so there are these medical knowledge bases which contain a list of treatments, list of diseases, and so on. And which is what we use to actually identify these entities, medical entities from the question. Okay. There's also this software called as MetaMap and CTEX, which basically also allow you to do medical NLP over these questions. Okay. So we did that, and then we ended up with for each of these different types. So for each of these different types, demographic or treatment and so on, we basically tried to figure out the scores for each of these entities. Okay, so that's that, and then we figured out the max score out of these. So for example, max 1 is 7.54, which is this one, and max 2 is basically 4.3, which is actually this one. So essentially, for each of these entities, we have the scores across these things. How did we basically obtain these? Well, for each of these entities, we looked at how many of the posts which contain CABG have been marked as treatment or have been marked as goal, and so on. And that basically gives us this distribution. Okay, so so that's that. And then by looking at max 1 and max 2, we basically sort of computed this factor, which is basically a division of max 1 and max 2. Okay, 1.75 is the R value. So this is what we did for each of those entities, which are mentioned in the question. We computed these R values per entity. And if this R value is greater than the threshold, we empirically fix this threshold as 1.35. Now again, we varied and then saw if the accuracy improves and so on. But we found that, hey, threshold of 1.35 is a good one. Okay. So if the R value is greater than or equal to the threshold, then we actually included the strength of association feature. So basically, so SOA is the strength of association feature. So medical features that we extracted are called the strength of association features. And then we said that for this question, the strength of association feature with respect to a particular class is +1. So essentially now the strength of association feature is such that it will be applicable across all categories. So for each of those categories, we have a strength of association feature. And if there are more entities with, which are very much aligned to that category, then we basically say that the question is aligned to that category, +1 for every entity that is aligned to the category. Okay, so that's that. So for example, for this category, 17.5 is greater than 1.35. Therefore, there is the SOA feature for this question for the treatment category is 1 now. Okay, and then similarly for this one, it's 1 because again 1.24. 1.24 is less than 1.35, so we ignore this entity. We don't care about this entity. Okay. The idea is that, hey, if a particular category is highly associated with the entity compared to other categories, so if these entities are really representative of this category, we want to consider this entity as contributing, as sort of associating the question to that category, right? So therefore, we ignore the second entity just because, hey, it doesn't really meet the threshold criteria, right? And then we did with this one. So again, this one predicts the highest one as 6.9. R is greater than threshold, and therefore we have 2 right there. And then we have 3 right there. It turns out all of them are sort of predicting, more or less predicting treatment as the category for this one. Okay, so that's that. Okay, so that's our SOA feature vector. So essentially, SOA features are basically a vector of the size of the category. Okay. Now, lastly, so we basically said we'll have 3 different things. So what is the term frequency? TF-IDF. Well, it computes how important a word is to a document in a collection or a corpus, right? So TF is term frequency. IDF is inverse document frequency. So for each of the words, we basically in the question, we basically computed a TF-IDF vector. Use those as features as well. Okay. So represent each question using TF-IDF vectors, and then architecture of the network is simple. Neural network with 1 FC layer, a dropout layer, fully connected layer, a dropout layer, and finally a softmax layer, right, for classification. So that's that. So now the question is, can we do something to increase the training data size? Because, hey, I mean, all this worked well, but our training data is rather limited. It's basically just a few thousand, so around 8,000 questions for training, right? So can you do something to increase the size of the data? Now, and we did that using weakly supervision approach. Okay, we crawled about 100,000 health questions from medhelp.org. So we went to this website, crawled all of those 100,000 questions, and use self-training to increase the amount of labeled data. We will basically talk about, this is how self-training really works. Okay. So you take the labeled data, small labeled data 8,000 that you have, train a basic classifier. Okay, you have a lot of unlabeled data, 100,000 posts. You ask the classifier to come up with predictions. So those which have very confident predictions in either of the classes, any of those 7 classes, right? You take them and put them back as part of your training data, retrain the classifier, make the classifier even more robust, better. Okay, because now the classifier has more data to train on, right? The actual labeled data and the data which it saw from, which it basically classified with a very good probability from the unlabeled part. Okay, so that's how self-training works. So you could basically increase your labeled data by using self-training technique. However, there is still problems with self-training. Okay, especially and this is an iterative technique, by the way. So you keep adding and then you retrain the classifier. You again pass the unlabeled data. Maybe there are more instances which are predicted with a very high probability in either of the classes, any of those classes, and then therefore you append them to the training data and you again rebuild the classifier and so on. You keep doing it iteratively. Now the problem with self-training is that in the initial iterations, a very weak classifier is deciding the label for the instances, and that's why if an error happens in the beginning, that error can propagate in further iterations, causing self-training to sort of drift the initial or dirty the training data as such, right, over iterations. So even small error propagation over iterations can cause significant issues, right? And therefore, we in this work we propose a self-training with lookups. Okay, it's a very simple idea, but it sort of works nicely. Okay, it stores prediction made for any unlabeled sample whose confidence is greater than threshold for the first time. So in fact, we use something called a lookup table. So let's say if you have 7 different classes, so you take an unlabeled instance, and you have this weak trained classifier. You ask for it the prediction. Okay, Well, if the prediction is, say, let's say the second class, you store that information in the lookup table. Okay. Now each category maintains its own lookup. So there is a lookup table where for each category you maintain it. Intuition behind lookups is to get double sure about our prediction. So now, when you again train the classifier in second iteration, if it still says that the category is that, you basically are more sure, or rather very much sure that yes, the category guessed by the classifier is correct. Okay. So analyze the current predictions made by the classifier based on its previous behavior. Okay. So if the classifier said twice that yes, this is the category, then you basically add it up to the training data. Until then, you just keep it in the lookup table. Okay, that's the basic idea. Okay. So the way we change the self-training thing is to basically take the labeled data, okay, train a classifier, come up with a prediction on unlabeled data. Predicted labelings, rather than just doing throttling, what you do is to keep it in a lookup table. Okay. So, predict the class for CR for I, and then if I is already there in the lookup table, if the category was already predicted for this instance in the lookup table, then you just add I to the labeled data in some senses. Else you basically just keep throttling, in the sense you just keep you basically add this particular instance I to the lookup table for the category CR. And you keep doing that. You basically don't add it to the training data. Okay. But yes, if this particular category for this instance I was already there in the lookup table, in the sense the classifier already said that yes, it belongs to this second class at least once. Okay. Then you basically check if I is equal to prediction of my. So in the sense that hey, if basically the prediction that was made by the classifier earlier actually matches now. If it does, then you basically get the size, and then you try to do the balancing a little, and then finally add the prediction to the training data. Okay. So the idea is that you also do not want to continuously keep adding instances to a particular class, because that then changes the balance of your overall data set, right? So therefore, it is always important to actually also keep the balance in check. Okay. Besides being doubly sure about the class label that you're assigning using self-training. Okay. So anyway, so even if you didn't get that part, the idea is that we used some modified version of self-training to actually increase the size of the overall data set, and then trained our ensemble model using this increased sized data set. Right. So so it has all the three parts that we discussed. This is the hierarchical hierarchical Bi-LSTM network, where there is a sentence encoder and there a question encoder. This is basically the strength of association based medical features that we have extracted from by using medical entities extracted using UMLS and MetaMap. Right. This is a TF-IDF based encoder. Okay. And all of them basically have contribute to the overall loss function. So we take all of these three sets of features and combine them at the top so as to get one concatenated feature set, which we connect with the output layer. Output layer is of size 7 in this case, because we want to predict one of the 7 classes. Okay. So that's that. We use cross entropy loss because multi-class classification, that's the most popular loss function, so as to train the entire network end to end. Okay, so all accuracy is computed on test size of size 300, which was provided by the challenge, ICHI challenge, right? So remember, there were like about 50-60 teams, and those challenge winners could get 68% accuracy. Okay, the winners in that challenge in 2016. Okay, and now we have our various techniques. So we just have Bi-LSTM, hierarchical Bi-LSTM. This is our strength of association based thing, TF-IDF. And we have combinations, so the ensemble of all the three. And as you notice, we have been able to get an accuracy of 69.76%. Okay, that's a boost of about 2% accuracy over the best guys who could do it in 2016. Okay, so classifiers were trained on the 8,000 samples only. We considered models proposed by these ACHI challenge winners as state of the art. Right, so. Especially in this ICHI challenge, the winners basically used typical TF-IDF and basically applied logistic regression, SVM's random forest on that, and also basically applied CNN. So basically the baseline is not that weak a baseline. It's actually fairly strong baseline that they have used. Again, 68%, 69% are not bad results given that it's a 7-class classification. A random classifier with the balanced data would have provided 100 by 7. Which is basically about 14% accuracy 14.2% accuracy in general, right? So this is much better than a random classifier, 68 or 70% accuracy approximately, right? So that's that. So these are the results of our weakly supervised model. So remember the previous slide just showed you without any weak supervision. So we did self-training with lookups and that outperformed the traditional self-training. Okay, so the technique that we propose. So we see that if you do with lookups or without lookups, usually you see somewhat better results with lookups. Okay, so and the highest accuracy of 71.13 is achieved using the ensemble model in the weakly supervised setup. Okay, so so basically, as you see in this table, if you actually also do this weak supervision, add more instances thanks to self-training with lookups, basically we obtain 71% accuracy. Okay, so outperformed all other models in the supervised settings as well, and also beats the current baseline model by a margin of 3.13 absolute percentage points. Okay, so that's basically the approach. So that's basically the results, and the nice part is that yes, the results beat the baselines pretty well. Okay. So we also did some error analysis, so just to figure out, hey, where are we going wrong? So of course there is room to improve. So in the sense there is about 30% cases to improve on. Okay, where are we going wrong? Okay, so sometimes the classifier fails to predict the most dominant class, and that sort of happens. When there is a lot of confusion in the examples. For example, this is a question. So last night I got high fever. My dad consulted his doctor friend. Okay. Now most dominant category is of course disease, but since it also contains the word dad, the predicted result is family support, right? So that's the wrong category, because there are certain words which are very much tied to the other category that it causes the classifier to get confused, right? Perhaps modeling the problem in a multi-label, multi-class classification setting will address these problems. So the idea is that although the label for this was completely disease, well, family support could also be a reasonable label, because hey, the dad is actually acting as a caregiver in this particular case. So those settings are called as multi-class, multi-label settings, where for every instance you could also have multiple labels rather than just one label. But well, the data that we got actually had only one label per question, and that is why we couldn't do multi-class, multi-label kind of classification, right? So that's that. So overall, to conclude, we proposed a novel approach to generate features using this medical domain. I mean, the problem that we wanted to solve was given a question, figure out one of the 7 categories. Okay, and we proposed this SOF feature-based approach, strength of association medical feature-based approach. We also proposed this self-training with lookups, which was a new thing to do. Usually people just do self-training to get weakly supervised data, but we did self-training with lookups and actually saw that this is better than just doing typical self-training. Okay, and finally our ensemble-based model, which combines domain knowledge using SOA features, lexical knowledge using TF-IDF representation, and also semantic knowledge using 2-level LSTMs, demonstrated the effectiveness of the method. So this is our final method, and surely it gave like about 3% boost over the baseline methods. Right. So that's all about this paper. If you want to read more about the paper, you can go visit, you can go find the paper by the title. Or also, if you have interesting things to talk about the paper, put them in the comments. It will be good to have healthy discussion about this paper in the comment section.